All right, so let's jump right in. Today we are taking a look at 6.1, which is a brand new chapter. It is our very last chapter. So those of you who have been on this whole STEM core journey for the entire academic year, this is the moment. We have hit the end of, almost the end of the class, and we are about to start our very last chapter. All right, so chapter 6 is all about taking what we've learned about integrals and applying it to different contexts, both in 2-dimension as well as 3-dimension. All right, so we're really ramping things up. We're not just looking at graphs in 2-dimension, but by the end of the week and for the rest of the semester, we're going to be looking at things in 3-dimension. I do want to preface this by saying that the jump from 2 dimensions to 3 dimensions can be really hard for folks, and that is completely okay. It is completely okay to be looking at a shape and being like, I don't understand how this turns into this other 3D shape. It takes a lot of practice, like a lot of the stuff we've been doing. It takes a lot of practice. It takes a lot of, well, for you folks, watching a lot of videos, maybe looking at some different animations to help you bridge that gap between a 2-dimensional space and a 3-dimensional space, okay? Yes, it is crazy how time flies. All right, so let's take a look at what we know. All right, so rooting ourselves always with things that we want to know, help us bridge that gap between everything new that gets layered on top of it, okay? And so what we've been doing so far is we've said, hey, we've got this graph and we are going to start at A and we're gonna go all the way until B, okay? And real quick, what kind of values are A and B? Are they like X values, Y values? What are they? Those are X values, right? And so we've got these X values and we've said, hey, go ahead and find the area from A to B between the curve and the X axis. And I'm wondering if someone can tell me the notation we've used, in fact, to talk about what we have here in this picture. So this area, how do we describe finding that area using calculus notation? Here we go. All right, we've got this integral from A to B of f of x dx. It is a notation we've come to know and love, or maybe not love quite yet. But when we say the integral, Monday morning integral signs, the integral, let's try that again, from A to B of f of x dx, that means that we're finding this area right here, right? That gives us our A. Okay. Now, I do have to share sort of a secret here. And this secret is that there's actually been something that we've been subtracting this entire time that I didn't tell you about. And so let's move this up here for a moment. And so here's the secret, that this expression that we have had actually been the integral from A to B of f of x minus 0 dx equals A. So that's the big secret, okay? There's been this -0 sitting there the entire time that we've never talked about. In this equation, does the 0 matter? No, it doesn't matter, right? We can take a function, we subtract 0, we still have the whole thing we've been working with, right? But I'm wondering if someone can maybe share a guess with me about where this 0 is on this picture. Okay, where is that 0 on the picture? Because I argue that that 0 is actually on the picture somewhere. Ah, all right. I should have picked better colors here. But yes, this right here is this 0. Okay. And so one of the equations that you may or may not remember from, I don't know, could be anywhere from middle school on, is if we think about what is an equation for just this line, we might say that this is y equals 0, right? Y equals 0 is another name for the line along the x-axis, okay? And so when we say y equals 0, that's this 0 that we've secretly been subtracting this whole time. But since it's 0, we never had to write it here, okay? However, the idea that we have an integral and that talks about area, that part is still the same, okay? And so here's the new part for 6.2, right? One new idea here is that now instead of having that bottom curve be the x-axis all the time, because that's kind of, I mean, it's kind of nice for us computationally, but it's kind of boring at the end of the day because there aren't as many applications of that. And so now what we're going to be thinking about is, well, what happens if we have our f of x function, which is right here, right? And separately, we have these colors. I don't know. I think we all kind of need the semester to be over. Okay, there we go. All right, so we've got two functions, right? We've got this pink one, we've got this orange one. And now we want to find this area that's right in between here, okay? And so based off of what we wrote over here, and perhaps in our secret notation, how might we represent finding this area right here? Okay, and I know that typing into the chat can be a little bit daunting once we introduce these symbols. How do we get that integral symbol again? One of those nerdy things that are probably helpful only in this class. But how do we type the integral symbol into the chat again? I forgot how we got that. Option plus B. Awesome. There we go. Okay, so maybe finding the area over here is actually just going to be very much the same. We'll have our f of x, and then we're going to subtract. So we're going to subtract the g of x, because now we don't have a 0 on the bottom. We have this other function g of x. And so if we grab that and write that here, we could say that this area is the integral from a to b of f of x minus g of x dx. Okay. And this g of x is the one on the bottom, and the f of x is the one on the top. Okay. And so that is a really great extension of what we've just looked at, where we're sort of rooting ourselves in what have we been doing this whole time, unveiling this secret, and then applying this new idea to the secret. Okay. Now, for those of you, and I know there were a few of you who are really curious where this dx comes from at the end of all of our integral symbols and like, why is it so important? And the dx is really, and I think we talked briefly about this, the dx is really like this delta x. It is really the width of every single rectangle that we have. And so when we're thinking about this notation, it's really important that we include that dx, because that tells us that we're going to have an infinite number of rectangles. And in fact, the rectangles are all going to be infinitely thin. So thin that the height of that rectangle, this height right here, we can find by taking f and subtracting g. That will give us the length between the two curves. And once we have that length, we're going to add them all up, all of them having the same width, and then we'll get the total area that we have between those two curves. Okay. And so that's really what we're going to be taking a look at today. All right, we're going to be taking a look at a lot of examples where we're looking at finding the area, not just between a curve and the x-axis like we used to do over here, but now we're going to be changing this bottom function to be some other function. Okay. So let's leave that for right now. And we're actually going to jump into an example first, and then we're going to come on back and we're going to fill in those boxes later. Okay. So the questions are going to look sort of like this. And I would have one really big suggestion for you, which is draw pictures. Draw pictures that relate the information in the diagram. For those of you who were in STEM Core in the fall, you know that we spent quite a bit of time on graph transformations and knowing what certain graphs look like. And that's going to be really helpful for us here in this section. Okay, so very much delayed gratification, but we're finally at a moment where we're going to be able to use our graph sketching skills to help us out. And so let's go ahead and get started with this example. Example 1 says, find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Now, I bet we all know what y equals x squared looks like. Okay, I bet we all know what that looks like. I'm wondering if you can tell me in relation to that, what is sort of similar or different about the second y equation? Ah, it is a negative parabola. I love that. It is upside down. Okay, okay. So we've got this equation. And we know that, wow, we know that this one looks something like this. And are we committing to yellow? I mean, to orange and pink? I think we might be. we've got this other equation, and we know that that looks something like that, okay? To kind of get a little bit more detail on this 2x minus x squared though, let's go ahead and factor out an x, all right? So if I factored out an x, what would still be left inside those parentheses? A 2 minus x, perfect, perfect. 2 minus x, okay. Now, before we graph these, because it's important to sketch them, but it's also important to sketch sort of accurately, okay? I'm wondering if you can tell me about the pink parabola, namely, what are the x-intercepts? Like, where does this parabola, the pink one, cross or touch the x-axis? Yeah, I believe that it does have an x-intercept at 0, 0. Okay. What about this orange parabola? Where are those x-intercepts? Hmm, 0, 0, and 2, 0. Now, where did you get those numbers from? You're 100% correct, but let's just make sure that everyone understands where those numbers come from. Precisely, precisely. So this piece where I was like, I don't know, let's just factor that and hold on to that for a little bit, was secretly like, when you factor, that actually helps you find your x-intercepts, okay? And so this idea of finding a factor and using that to find the x-intercepts is certainly going to be a very useful skill, okay? And so now we know we've got an upward facing parabola. We know that it has a x-intercept at the origin. And then we have this downward facing parabola that has two x-intercepts, 0, 0, and 2, 0. And so with that information, let's go ahead and sketch a graph of this so that we can kind of see what we are trying to find the area of. Okay. Now, I know that the pink parabola maybe looks something like this. And that satisfies my x-intercept at 0, 0. And then I have to draw the orange one so that it crosses at 0, 0, and 2, 0. And so that might look something like this. Oh, that second parabola is definitely much better than the first one. Okay, so now we've got our picture. Okay, let's label some important points and let's see. So we know that this point right here is 0, 0. Okay. My question to you is, how do we find that second intersection point? Right? We know that one of those intersection points is 0, 0. How in the world do we find where that second intersection point is. Okay. So this is perhaps a skill from like pre-calculus, where we wanted to find where any two graphs meet. And anytime that two graphs, or more than two graphs, but in our case, two graphs, anytime they meet, what we're saying is that the y values and the x values of those points are exactly the same. And so what we're going to do here is we're going to take, so to find intersection points, we're going to set one function equal to the other function. Namely, we're going to have the pink one equal to the orange one. Okay, so we're going to have the pink one equal to the orange one. That right here is one of the most useful processes or algebraic structures that we're going to use as we move through these problems, okay? So to find the intersection points, we want to make sure, so we have sketched a picture to find the intersection points. We're going to set them equal to each other and then solve. So let's go ahead and do this. How would we solve here? This equation that has the pink x squared equals the orange 2x minus x squared. All right. So my hope is that for those of us who are not answering these questions, that we are perhaps mumbling them to ourselves in our sleepy state at home, because these are processes that we want to be like, okay, yes, this is in my toolbox. I understand how this works, okay? So being able to sketch a graph in number one, super important skill. Being able to problem solve, how do I solve for something without someone telling me how to solve it, also an important skill, okay? And so let's take that idea, let's put everything to one side, let's set it equal to 0 and factor. All right, so I'm gonna add things, I'll get 2x squared minus 2x equal to 0. All right, and when we factor this time, right, when we factor this time, we actually can pull out not just an x, but the greatest common factor here looks like it's going to be 2x. And so we'll have 2x in parentheses x minus 1 equals 0. And now we're able to find our intersections, okay? So one of them, I can say 2x equals 0. The other one, I can say x minus 1 equals 0. Yeah, it's not quite the y-intercept, all right? It is, in fact, our intersection point, but it is the y-intercept of this graph, which is not our original graph, okay? And so if I solve each of these mini equations, I'm going to get x equals 0, and I'm going to get x equals 1. All right. And so yes, exactly, 0 divided by 2 and then 1. And so we already knew that one of the intersection points was 0, right? That means that this point right here must have an x value of 1. So we've got this x equals 0 is this x equals 0. And this x equals 1 is this one, okay? Now, question, how do we find the y value that goes with that? Okay, we can plug 1 in. Does it matter? What equation should we plug 1 into? Because we have a lot of equations going on here. Where should we input the 1? Either one, they're the same, right? So we could choose the pink one or we could choose the orange one. And like Natalia said, let's just choose the more simple one, the pink one, right? So we're going to plug in 1 in there. 1 squared is 1. So the y value here is 1. Okay. And so all of this algebra and graphing, all of this, I know, should feel familiar. Okay, maybe not like in the recent past because we've been working so hard on our integrals and derivatives, but somewhere back in that brain, we've seen this sort of stuff before. Okay, yeah. And for those of us who are from STEM core, this is like August through October of last year. So that's like a lifetime ago, right? A lifetime ago. Okay, so here's what we found, right? We found the intersection points, but we're looking to find the area, right? We're looking to find this area right here. And so if we think about it, we want to use an integral, but in order to use an integral, we're going to need bounds. We're going to need to know where we start finding the area and where we stop finding the area. Okay. And so now I believe we are finally ready to go ahead and set up our integral. So now this part is the new part. Okay. So if we want to find the area, then we're going to have to set up an integral from a to b of f of x minus g of x dx. And that's just a general formula, okay? Look at that for a moment, embrace how much you've grown as a mathematician, that this is now the quote unquote basic formula that we're gonna plug things into, okay? And so when we think about that, what might we put in for our A and what might we put in for our B as it applies to this particular function or picture? Little a is 0, good. I know. I thought about that too. I was like, pretty sure he knows that area is not 0, but then I forgot it autocorrects. And b equals 1, good. Okay, now Josh, you put something in the chat. You said that the 0, 0, and maybe you would guess 1, 1. And so we're going to come back and fill this out in that little chart above. How do we know which value to use? Okay. And so in fact, I'm going to go back here and I'm going to erase this random scribble for the purple. And I'm going to draw it a little bit differently. Okay. I'm going to draw it with a bunch of rectangles, and in specific rectangles that are so thin, I could maybe just draw them as a line. So I'm going to draw one rectangle like this. And I'm going to draw another rectangle like this. They could be closer together, maybe they're further apart. The reality is there's an infinite number of purple rectangles. Okay. Now these rectangles though, do they sort of stack up along the x-axis or do they stack up along the y-axis? Maybe let me draw these lines one more time. And as I draw them, think about that question. Do these rectangles stack up along the x-axis or along the y-axis? Okay. So like one little rectangle, two little rectangles, three, maybe 4, 5, 6, 7. And so these purple rectangles, as I'm drawing them, Josh is correct. They are going along the x-axis. Okay. This idea right here is stupidly important. Okay. It's like for the rest of the month that we have together, we will continue to use this idea that if you draw these rectangles, do they stack along this axis or that axis? Okay. So the ability to draw little lines like this is actually incredibly valuable. Okay. So yes, you were correct. Everything stacks along the x-axis. And so as such, we don't want to grab the whole point. We only want to grab the x value to start and then the x value where to stop. Okay, so even though in this case the numbers are the same, like it's 0, 0 and 1, 1, we choose the x version of that as our bounds because all of these rectangles are adding along the x-axis. Yes, Ethan. And we're going to move into a place where they're not always on the x-axis. Yeah, I know, so many secrets that we haven't talked about yet. All right, so let's get these bounds in here. The bounds correspond to the blue 0 and the blue 1, okay? All right, now, how do I know which function is f of x and which function is g of x? Because, I mean, Judy was certainly not helpful. She just called them both y. So how do we know which one is f of x and which one is g of x? And if it's helpful, I can scroll back up to our what we know versus what's new. So if you'd like to see that screen again, let me know. I'm happy to scroll back up so we can look at that to maybe help make our decision. Yes, okay. All right, so remember, we're trying to decide which one of these y's should be our f of x and which one should be our g of x. So. Okay. These are great observations. Orange is g of x. Okay. So the important thing that I want us to take away from this picture in particular, wow, that's an aggressive zoom, but the important takeaway, okay, is not that I call one of them f of x and one of them g of x. That's actually the least important part of this. Rather, the thing we want to think about in our patterns is more along the lines of what Ethan is saying. Which one is on the top? And same thing, Megan, which one is on the top and which one is on the bottom? Okay, so when we go back and summarize this, when we write our equation, we're not going to necessarily put f of x and g of x, but rather we're going to put the top function minus the bottom function. Okay, so we're not rooting it in one of them has to be f of x and the one that's g of x is on the bottom. We're saying whatever's on the top goes first, and then we subtract whatever's on the bottom. Yes, Josh, that's a great way of thinking about that. So here, notice how this f of x is the top part of the rectangle, whereas the g of x is the bottom part of the rectangle. Okay, so instead of thinking f minus g, we really want to think more like top minus bottom. Okay. So with that, let's go back. What are we going to call our f of x? What are we going to call our g of x? Yeah, I think that's another way of saying the same thing, because f needs to be that bigger one. Exactly. And maybe we could even say the more positive one. That would be okay too. Are you perhaps looking at an older version of notes? Because we don't have a green parabola here. All right, so we've got one guess that y equals 2x minus x squared, that orange parabola. I would say yes, that is indeed the top function. So we're going to put in place of f of x, we're going to say 2x minus x squared. All right, now we've got our f of x minus, that means that our x squared must be our g of x. I am going to put parentheses around this. Okay, why would I want to put parentheses around this? I don't think it matters here, but what might I be afraid that if we don't put parentheses here, that you'll forget to do, and what kind of mistake might that lead to? Okay, maybe combining those, that could be one mistake. I might also imagine, let's say that there were like, more terms here. Maybe I would forget to distribute that minus sign everywhere I needed to, right? That's a super common mistake. So put these parentheses here. If you don't need them, then they just go away in the next step anyway, okay? So now, before we take our integral, let's make sure that we're going ahead and simplifying this first, okay? Do yourself a favor. Simplify this integrand before you start taking the antiderivative, okay? So we get the integral from 0, so small, 0 to 1. And if I get rid of all the parentheses, I get 2x minus 2x squared dx. All right. Now let's go ahead and find that antiderivative. What do we get when we find the antiderivative of 2x? And what do we get when we take the antiderivative of negative 2x squared? So let's do those computations and then throw those into the chat. Perhaps some folks could take the 2x and some folks could take the 2x squared. And then we have our bounds 1 and 0. Okay. All right. Now, for better or for worse, even though these questions are have a much more of a setup, the nice thing is that the integrals that we do tend to be more straightforward. Okay. So the integrals here won't necessarily be as gross as the ones that we saw in the previous unit. All right, let's plug in our bounds. Do we plug in 1 first or do we plug in 0 first? We plug in that 1 first, good. So I'm gonna get 1 squared minus 2/3 minus 0 squared minus 0. And we'll get 1 minus 2/3, which gives us 1/3. Okay. And so the area of this part right here is exactly 1/3. Right. So there's that whole problem on one page. We'll get to bigger numbers later. Don't be too disappointed. The last few weeks of Calc 1 are definitely not always so easy, okay? But we do want to kind of embrace the idea here and the decision making. That's perhaps the most important thing, okay? All right, let's do one more example. and see. Okay, so we've got this question: determine the area of the region between the two curves. We have one curve that is x squared minus 24, and we have a second curve that is y equals 1. Okay. Will the bottom bound always be the one that is further left on the x-axis? When we're dealing with a situation where the rectangles line up along the x-axis, yes. However, if the rectangles line up along a different axis, then no. Okay. All right, so let's do our algebra setup. We're gonna draw some pictures. We're gonna find some intersections and see what happens. I don't know if you just heard that little snorting noise. That was my dog back there. Apparently she is super excited for this algebra stuff. Okay. So we've got a graph and we're going to want to find intersections. Okay. All right, tell me about that pink curve. What do we know about that pink curve? It is a parabola, facing up or facing down? Facing up, perfect. And what about that minus 24? Shifted down, how many? 24, there you go. Okay, so all of that graph transformation stuff that we did, a lot of it boils down to some of those simple cases. It's just a vertical translation. Or you factor it, it factors out so nicely. You just have to know if it faces up or faces down. Okay. So if we go ahead and sketch this, then we have, I don't know what's going on today. Okay. We have a parabola like this, and we could mark this point here as 0, -24. Okay. All right, tell me about that orange, not the green. Tell me about that orange function, y equals 1. What does that look like? It's a horizontal line at 1. Excellent. So this diagram is clearly not super to scale, but let's just throw that there. And we've got our line, y equals 1. Okay. Now, in order to figure out my area situation, I have to know where to start and where to stop. So we need to find some intersection points. How do we find those again? What's sort of our mantra about finding intersection points? They're the same, they're equal, we set them equal to each other, right? However you want to remember that. So I'm going to take my pink function, x squared minus 24, I'm going to set it equal to the orange function, which is just 1. Okay. All right. How can we solve? How do we get x by itself? Move them to one side, set it equal to 0, and generally, but not always, factor. All right, so x squared minus 25 equals 0. This is a very good factoring that we want to know, okay? I think it's a structure that comes up quite a bit. How do we factor x squared minus 25? X plus 5, x minus 5, brilliant, x plus 5, x minus 5 equals 0, and we get x equals -5 and x equals +5. Okay. Yes, exactly. All right. So that means that the x coordinate of this point right here is -5. What is the y coordinate of that point? Right. And I have 5 comma something. 1, good. 1, 1, because they're both on that orange line, which means they both have a y value of 1. Okay. Now, before we set up our integral, let's draw some rectangles. Okay. So if I were to draw rectangles, and I would say this is a good way to sort of start and try drawing them the way we've been drawing them and see if that works out. Okay. So maybe this is one rectangle here. Maybe this is another rectangle, another rectangle, another rectangle, tiny rectangle, right? And these purple rectangles, do they line up along the x-axis or along the y-axis? They line up along the x-axis. Okay, now that is correct. And ask you a true or false statement. Okay, so in the chat, you're going to type true or false. So true or false? Every purple rectangle has the same function on top and the other function on the bottom. True or false? Okay. Every purple rectangle drawn here has the same function on the top and the same function on the bottom. Yeah, in particular, which function is on the top? Y equals 1. Okay. So in addition to drawing rectangles, because I could draw them differently, okay, knowing whether you drew your rectangles correctly or not is about asking yourself that very question. Does every rectangle have the same top function and the same bottom function? Okay, because once you have that, you have your f of x and you have your g of x. Okay, so let's set up our integral. To find the area, we're going to integrate from a to b of top function minus the bottom function. And which axis did we stack along again? The x-axis. So we want to say dx. Okay. All right. What can we put in for our a and what can we put in for our b? All right. What number do we put in for our a? What number do we put in for our b? -5 and 5. Good. Okay. Our top function is the orange one. So we're going to put 1 minus the bottom function. Oh, parentheses are definitely going to be important here. X squared minus 24 dx. And so this is our top function in this case. And this is our bottom function in this case. All right. Okay, so we're going to simplify. We're going to simplify this integrand. And let's also do a shortcut, okay? Look at this picture that we drew. If I fold it in half, along the y-axis, will the two halves match up? Yes, right? If you fold this in half along the y-axis, you're going to get the same thing on both sides. Exactly. Now, I am perhaps, I don't know, I do like shortcuts, specifically in calculations. I like to make things easier for myself. And so what we're going to do is we're going to say, let's simplify this inner function. We'll get 25 minus x squared dx. Okay, so that's just combining the orange and pink to make 25 minus x squared. I'm going to keep the top bound, but I'm going to change the bottom bound to 0, as Yithan has suggested. That means that I'm just going to take this area, okay, the one on the right-hand side, and I'm going to say, let me find that, and then let me double it so that I find the total area, okay? What would be a different way that I could set up an integral so that I use symmetry? Like, how else would I set this up so that I'm going to use symmetry? -5 and 0, good. -5 and 0, and I could double this, okay? That would be totally fine. But if we're making things easier for ourselves, do we really want to throw in a negative number that we have to plug in? I'm going to say no, right? If we're already, like, if the purpose of this is to make it easier for ourselves, why don't we go ahead and avoid the one way that's going to keep like the negative numbers, which is oftentimes the hardest part, right? Let's instead pick something that has a 0, which is always nice to plug in, and a positive number, right? So it's not that this is wrong, but I doubt you'll ever see anyone use symmetry that way because it just doesn't make our computations quite as easy, okay? All right, so now the hard part is over. Now we just rinse and repeat. All right, so 2, let's see, integral of 25 was 25x. Integral of x squared is x cubed over 3. We're going to plug in 5. We're going to plug in 0. It's 2 times 25 times 5 minus 5 cubed over 3 minus 0. And let's see what we get. So we get 2 times 125 minus 125 over 3. Let's go ahead and combine fractions here first before we double things. So if I have a denominator of 3 over here, I need another denominator of 3. So my numerator becomes, what does that become? What does my numerator become if I'm looking to have common denominators? $375. There you go. All right. So 375. All right. What is my numerator here then once I combine the fractions? $250, good. 250 over 3. All right. Ooh, last step and last line before the page ends. What is our answer? 500 thirds. There you go. 500. 500 thirds. 500 thirds. What is that number? that number is the area between the parabola and the x-axis, parabola and not the x-axis, but that line y equals 1. Okay. You can certainly do this without symmetry, but I just make a lot of mistakes when I do that, and I don't like spending my brain power on that. I would rather be clever and have to do less computations. Okay. What if is the area if the x-axis were the shape of g of x instead? Yes, exactly. Okay, so let's do this. I think now is a great time for a break. All right, when we come back from break, we will fill in this part. All right. We will maybe set up some other questions. I don't know that we'll get a chance to work through all of them, but we will also spend some time taking a look at what happens when we switch things around. All right. So again, adding to that decision-making piece, like, why is she asking us to draw these rectangles? Seems like such a small thing. And why is she asking us if they go along the x-axis or the y-axis? Okay, so those are all going to be questions that we answer in the second half of class. Okay, so before break, we took a look at a few different examples. And we're going to sort of summarize those in our with respect to x box here. Okay. And so what I think would be helpful is noting a few things. Okay. In particular, we might notice that these rectangles are perpendicular to the x-axis. Okay. So these rectangles that we have are perpendicular to the x-axis. And so when I was saying, do the rectangles stack along the x-axis or the y-axis, that was really what I was looking for, is that are these rectangles perpendicular to the x-axis or the y-axis? Now, if that is the case, okay, then we can set up our area formula the way we've been doing. The integral from a to b of the top function minus the bottom function. Now, this is sort of a big deal here, but because the rectangles are perpendicular to the x-axis and we're integrating with respect to x, we want to seal the end of this equation with a dx. Okay, so when we have a dx, that means we're saying with respect to x. It might be helpful to note here that a and b are x values. Okay. And not always, but most of the time, when someone wants you to solve this question with respect to x, you'll notice that given equations are typically of the form, sorry, my handwriting, given equations are typically of the form y equals things with x. Okay. So if you see like y equals blah, 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 or f of x equals blah, 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 then the question is really hoping that you're going to have rectangles that are perpendicular to your x-axis, and that you'll have an x here and an x number here. You'll have a dx at the end, and these equations in here will have x's in them. Okay. So kind of like when we were doing our u substitution, we wanted everything to have u's. We want everything that we have here to have x's in them. Okay. All right. So let's do this. Let's do let's do a few more setups where we won't finish the whole problem, but we will set things up using this idea. Okay. All right, so find the area of the region bounded by the curves y equals sine x, y equals cosine x from 0 to pi over 2. So let's go ahead and we're going to sketch a graph. We're gonna find some intersections, and then we are going to set up our integral for the area, okay? I will leave the computations of this up to you in the privacy of your own home, but we will go ahead and set things up so that it's more just like the computational piece that you need to work on at home rather than the conceptual piece. Well, I mean, you're at home right now, but you know what I mean. Okay. So I've got this graph. Let's go ahead and say we have a graph of sine. We have a graph of cosine. And we want to graph this from 0 to pi over 2. Okay. So sometimes they'll tell you, hey, this is where I want you to start counting, and this is where I want you to stop counting the area. Whereas in the other ones, we actually had to find those starting and stopping point. Okay. So problems do give you different kinds of information. Okay. Beyond the fact that sine is squiggly and cosine is squiggly, let's really root ourselves in like where they might have a local maximum or a local minimum, or where they might have x-intercepts to help us sketch these graphs. Okay. Now, normally we go from 0 to 2 pi. That's sort of how we normally handle things. But just for the sake of this, because I know I only want the area from 0 to pi over 2, let's just graph from 0 to pi. And so this sine graph, what is sine of 0? Let's kind of use some points to help us out. What is sine of 0? Sine of 0 is 0. So this pink graph is going to have its first point at 0, 0. Okay. What about at pi over 2? What is the sine of pi over 2? Sine of pi over 2 is 1. Good. And sine of pi, where does that get us? 0. Okay. So I'm going to go ahead and mark off a 1 here and a -1 down here, because we don't expect for there to be values greater than 1 or less than -1. Okay. And so we've got our 1 and our 0. And this is just that first bump on the sine graph. Okay. All right, let's do the same thing for cosine. Cosine of 0, cosine of pi over 2, cosine of pi. I agree, it starts at 1. Cosine of pi over 2 goes to 0, and cosine of pi is at -1. Good. And so we have this. No, we have this situation happening here, okay? So we have that as our graph, I don't like that, that's, okay. So we have this as our graph. And going back to the question, we know we only want to find the area from 0 to pi over 2. And so that means that we're going to start counting our area at 0, but we're going to stop at pi over 2, okay? Now let's draw some rectangles, all right? Now I noticed that the equation has like y equals some things with x, y equals some things with x, and they even give us x values here. And so all of that is leading me to believe that I should be drawing my rectangles perpendicular to the x-axis. Okay. So let's try it. Here's one rectangle. Here's another rectangle. Here's the next rectangle. Here's a tiny, tiny rectangle. Okay. So let's pause for a moment. All of the rectangles that I've drawn so far, do they have the same function on the top as they do on the, and then separately, do they have the same function on the bottom? Yes, okay. So if you were to set up this integral right here, you would have your integral from a to b of the orange curve minus the pink curve, right? Orange is on the top, pink is on the bottom of that rectangle. So therefore, we would say top minus bottom or orange minus pink. Okay. Let's continue with our rectangle drawing though, because we got to get to this other blue line. One rectangle, another rectangle, one of the last rectangles. Do the second set of rectangles that I drew have the same top and bottom functions as the first set? No. All right. So this is one of the common plot twists, right? That we have rectangles. They're all perpendicular to the x-axis. So we know that we're integrating with respect to x. However, we can't just use one integral. How many are we going to need? We're going to need 2. One for each case where here it's going to be orange minus pink, but here it's going to be pink minus orange. Okay. So when we set up our integral in just a second, we'll make sure to do that part. Now, typically our step 2 has been finding intersection points, but in this case, maybe since the bounds are already given, what might be useful to know in our picture? Like we already have where we're starting and where we're stopping, but what might be an additional piece of information that would help us move through this problem? Knowing where they cross precisely. And so what we want to think about is, where do they cross? Because where they cross is going to help us set up our bounds for the 2 integrals. Okay, so since the bounds are already given, let's just find the intersection point in the given interval. Okay. We could certainly do this algebraically. We could say, hey, we set sine and cosine equal to each other. Sine of x equals cosine of x. What else could we do? What else could we do to find that intersection point? How do we know that it's exactly halfway between? I think you're on the right track, but just convince me, how do we know that that intersection is exactly halfway in between? I mean, I know my picture is beautiful and all, but like, we don't always know these diagrams are to scale, right? How do we know for sure that that intersection point is halfway between 0 and pi over 2? Okay. So one way we could do this, we could certainly say, let me solve this algebraically. However, there's a reason why instructors, specifically those who teach trig, are like, you have to know the unit circle. It's just nice, okay? If we think about just the first quadrant of our unit circle, we have sort of like this, okay? And we know that this is 0, this is pi over 2, but in particular, there's a special angle here, pi over 4, where the x value is root 2 over 2, and the y value is root 2 over 2. Okay, so it is completely fair game to say, yeah, I know that they cross at pi over 2 or pi over 4 because that's where these two are the same value. Okay, that is different than saying, oh, it looks kind of halfway in between. So if you do sort of make this claim, just make sure that you justify that somehow, right? But we can in fact say that this is pi over 4, okay? All right, so we've done our diagram, we've done our bounds. Let's set up our integral. Okay, so my first integral, I could say, is from 0 to pi over 4 of cosine x minus sine x dx. So cosine being the top of the purple rectangles in that part, and sine being the bottom of those purple rectangles, right? So top minus bottom, there we go. Plus, what is our second integral? Tell me what the bounds are. Let's start there. What are the bounds? What are those bounds? Pi over 4 to pi over 2. Good, very nice. And what do we change about our integrand, the part where we find our... Oh, does it really? Option plus pi? option plus RP. Yeah, exactly, Josh. We're going to have sine x minus cosine x because for that second half, sine x is the top of those purple rectangles and cosine x is the bottom of those. Okay. So we've got these integrals. Now, when you solve this at home for some extra practice, what might be a shortcut way that you could evaluate this? You could certainly practice setting up both of these, finding the integrals, plugging in your your bounds, pi over 4, pi over 2, or 0. But what could be a more clever way to move through this question? They're the same area. Good. So let's just pick one of them and let's double it. Do we want to pick the first one or the second one? Okay. Yeah, I generally like having the 0 there. So if you are looking at any of the answer keys, I will probably choose the first one or the one that involves 0 to double. You are welcome to do whichever one, this one or this one. Okay. I think in the sine and cosine case, it really boils down to which trig values you know a little bit better. Okay. All right, so let's kind of stop there. I'll let you compute through this on your own time. Let's see, but a goal answer is 2 root 2 minus 2. That is your goal. Okay. So when you work through this for some extra practice, that should be the answer that you achieve. All right. Now, I know that example 3 was a little bit different from the other examples. How do we feel about the things that made it different? Like, for example, finding the intersection right here, or splitting this into one integral and a second integral. Like, how come we needed that? Are we okay with that part of the decision making? You can give me a quick thumbs up or send me a message. A good question to ask yourself would be, do I know when we need one integral versus when I need more than one integral? Okay. So a couple questions. Let's see. Does that concept not apply? The second. I don't know that that concept particularly applies here. I think that's a great question. So the question was, if we just did from 0 to pi over 2, would we get 0? And yes, you would get 0. But it's more because you sort of, the negative part comes from, like, if you take this and you factor out a negative sign, you'll end up with that.
Wait, okay, now I'm confused because I was thinking, so you know how if we, is my voice coming?
I see another question. If we have a graph where we can clearly see the intersection point, do we still have to justify the intersection point? I would say that if the graph shows you the point, like on some of the WebAssign questions, they show you the point, that's absolutely fine. I will tell you that I'm not likely to give you an intersection point on an exam. So it would be good practice to figure out how to find said intersection points. Okay. All right. So maybe as sort of a general statement, let's draw a picture of when do we need more than one integral, okay? So when do we need more than one integral? Great question, okay? So when do we need more than one integral? Well, if you look at your picture, okay? So let's say that we had a function like this, and then a function like that. And if I choose this interval from here to here, do we need one integral or more than one integral? So we're trying to find the area here. So we might have something like this for our rectangles. Do we want one or more than one? Only one, right? Okay. Well, what if we had, well, let's write that down. Only one. Let's say we had something like this. One integral or more than one. More than one. Good, good, good. Because I have these ones here where the pink one is on the top, but then at a certain point it switches and now the orange one is on top. So I need for this question 2. Okay. What if we had a situation like this, and I wanted to start from here and go all the way to here? How many integrals would I need? How many would we need there? 4, that's one guess. Anybody else have a different guess? 4. All right, well, let's take a look. It looks like this region has some. That's 1, 2, 3, 4. Yeah, I would say that this one has 4 separate sections. So we're going to need 4 integrals. Okay. So anytime you switch, having sort of one on the top and one of the bottom, and then that switches, then we're going to need a separate integral. Okay. Now, sometimes we can say, just like we did here, hey, we know that this one is the same as this one, so we're just going to double it, the first one, and call it a day. Okay. So that idea of symmetry definitely cuts down on the computations quite a bit. All right. But I think this picture right here, hopefully will give us a better understanding of when we need to use what. Okay. I do want to set up number 4, because I think sometimes it's not always exactly halfway. And I think example 4 is a really good showcase for that. Okay. So Find the area of the region bounded by the curves y equals cosine theta and y equals 0.5 from 0 to pi. And so let's go ahead and set up our diagram and what other information we might need. And so I'm going to go ahead and draw our x. What is happening today? Draw our x-axis, the y-axis. All right, and let's again maybe just go from 0 to pi. You know, it's kind of weird to draw like half of a trig function, which is why I think like my graphs maybe look weird. All right, but we have that one. We have this one. Okay, so cosine we know from before is going to be 1, 0, -1, and sort of looks like this, and like this. Okay. And then y equals 0.5. Well, I know that this is 1, so 0.5 is probably somewhere here. And if we draw that, we know that, as I think Chant said earlier, when we have y equals something, it's just a horizontal line at that value. Okay. Now, if we think about the bounds that they gave us, 0 to pi, that means I'm starting here and I'm actually ending right here. Okay, so I'm starting at 0, I'm ending at pi. Now, based on our sort of previous diagram, how many integrals will we need here? 1, 2 more. How many do we think we'll need? 2. Excellent, excellent. Because if we look at this and we draw our rectangles, right? We have some rectangles here, little bitty one, right? We have those rectangles where the orange is the bottom function and the pink one is the top function. But as soon as we get to that intersection point, they switch. Now we've got the orange on the top and the pink on the bottom. Okay, so that means we're going to need a separate integral. Now, as before, though, we got to find that intersection point. And I think it might be really clear from this diagram that that's not pi over 2. It's not halfway, right? And so what we need to do then is say, where does cosine theta equal a 1/2? That's really what we're saying. We're still setting our two equations equal to each other. Okay. What is that angle? Theta equals pi over 3. Very nice. All right. So that means that the x value of this point is pi over 3, and it has a y value of 1/2. Okay. So let's just set up the integrals. What might those integrals look like? And I'll give you a number, a target answer, so you kind of know what to go for. But let's set up that area. All right, we already know we need 2 of them. So what do we do? Okay, I could do the integral from 0 to pi over 3 and then pi over 3 to pi. Good. So 0 to pi over 3 and pi over 3 to pi. And our functions, we're going to have the cosine theta here minus 1/2. And then over here, I'll have 1/2 minus cosine theta. Okay, so they just switch. Top over here is actually the bottom over here. And bottom over here is actually the top over here. Now, what do I write here at the end? D theta, love it, love it. So we're gonna have a D theta and a D theta just to keep in line with our notation, okay? It's just one of those things, it's such a small thing, but sometimes people don't explain to you where that comes from. And then you're like, how are we in a different variable all of a sudden? It really just depends on how that question is asked, okay? But great intuition here. Now, in this case, because the areas are not symmetric, I can't just pick one and double it. That would be a bad move, okay? I do have to work through this one, each piece, find that area. But at the end, after all of your computations, your target answer is 5 pi over 6 plus root 3, okay? So these, you are now entering a world where these are considered quote unquote nice numbers. I know you can scream a lot inside about it, but these are now nice numbers. Welcome to the next phase of your life. Okay, so how we feeling with that decision making? Like, how do we know when we need more than one integral? I feel like that's going a little bit better for folks. Yes, no, maybe so. Good, good. Okay. And okay, finding intersection points. Question mark. We okay with finding intersection points? Good. Okay. All right. So let's go ahead and so we're gonna skip number 5. Though I would certainly recommend that you take a look at that later. I will tell you that the answer is 10 over 9 plus natural log of 9. Okay. I think this is a good one to practice your integrals, especially if chapter 5 felt a little challenging. I think practicing some of the sort of more basic integrals would actually be a really good thing. Thinking about what these graphs look like and sketching those, I think, will also be helpful. Okay. All right. There are let's skip a few. Come back to that one if we have time. Okay, let's actually take a look at example 8. All right. Now, what are some things that you notice that are different about example 8? How is this different from the examples we've taken a look at before? They are y equals instead of x equals. Fantastic. Okay. So let's go ahead and draw some pictures. Now, those of you who had graphing calculators in high school, I think one of the terrible things about graphing calculators is that you had to solve for y every time you wanted to put an equation into the calculator, which is great practice and all, okay? Totally great practice. But sometimes feels a little like a lot of extra work. One of the beautiful things about Desmos is that you can type in equations of this form. Doesn't have to be y equal, okay? So if you are on a computer, I know that not everyone is, but if you are on a computer, pull up Desmos and go ahead and graph these two. And let's see what they look like, okay? They'll give you a moment to do that. Let's just kind of graph them, see what they look like. Is this the moment we're all awkwardly waiting for someone else to do this in Desmo? Nah, I'm just teasing you. I know it takes a while to kind of pull up a different website, but are we getting things that kind of look like sideways parabolas? Yes, okay. So let's start with this one, okay, the pink one. See how we could really write that as like y squared minus 9? Right, I could say x equals y squared minus 9. And if I thought about what I know about parabolas, okay, and I think Thea said earlier when we had like x squared minus 24, that it was a parabola shifted down by 24. We can use that same idea here, where it turns out that this y equals x squared minus 9 is a sideways parabola. And which direction is considered negative when we're thinking about side to side? The left, exactly. So this turns out to be a parabola that is shifted 9 units to the left. That's it. Okay. So if we kind of sketch that out, we'll end up with this as our parabola. Okay. Now, I think that if we approach the other one the same way we did in the first part, y parentheses 7 minus y, we're not looking for x-intercepts anymore. Rather, we might notice that the y-intercepts, because it's a sideways parabola, are 0, 0, and 0, 7. Okay. So if I were to sort of graph these on here, I might have a 0, 0, 0, 7. Which way does my parabola open? Like, does it open the same way as the pink one, or is it the opposite of the pink one? It's going to be that opposite. And this negative sign right here, that tells us they're going to be the opposite, okay? And so, oh gosh, let's see how we can actually draw this. We're going to end up with something kind of like, okay, that wasn't so bad. We'll consider that a redemption of my earlier diagrams. Okay. Now this whole time I've said, let's go ahead and draw rectangles. And every time I've said draw a rectangle, I've always drawn them vertically. Okay, so let's try this. One rectangle. That one has a top function that's pink and a bottom function that's orange, right? Does this second rectangle have the same top and bottom function as the first one? Like, does this, let me draw it again. Does this one have the same top and bottom function as this rectangle? Yeah, I would say the pink one's on the top, the orange one's on the bottom. Okay. What about this one? Pink on top, orange on bottom. Great. What about this one? Yeah. Okay. Here's the challenge. I claim that this is not always true. So I would like you to draw a rectangle, a vertical one, where the top and bottom functions are different than all the ones we've drawn so far. Bingo, there's one, there's another one, there's another one. Perfect. Okay, so when we kind of get to the ends of this function, right? In fact, this is so problematic. Let's see, this one right here, And these ones down here are exactly the problem. That what we said about the purple ones were only true for the ones we drew, but we could draw some where all of a sudden the orange is the top and the bottom, or the pink one is the top and the bottom. Well, if I take this function, 7y minus y squared, and I subtract 7y minus y squared, what do I get? I get 0. Well, that's clearly not an area of 0. So maybe, just maybe, this is not the best way to draw a rectangle. So let's redo this. You all made a great observation. You said, what's different about this problem? It's x equals, it's x equals. And when we said, when it was y equals, we said we want to draw the rectangles along the x-axis. Turns out when we have an x equals, we actually want to draw them along the y-axis. So let's try this one. What about this one? And this one? This one and this one. I don't think those have the same top and bottom functions. But what do they have? What do all of these purple rectangles share? The same left and right functions, okay? So I forget who it was earlier said, is it always going to be a certain way? And the answer is always no. We have to be really careful when we say, is something always a certain way in math? Kind of like, I don't know if you get into arguments with your significant others and you're like, you always do this, or you never do this. Bad choice of words. Nobody always does something or never does something. So we can say, think about this more like we have to learn how to make this decision. Okay, and one of the indicators here is that when the equation is x equals and the other one is also x equals, and you look at the picture and you're like, wow, that's kind of sideways. All of those, well, maybe arguments with parental figures, lots of things, you know, people like to accuse each other of always doing something or never doing something, but it's kind of like telling someone to calm down. That usually does not work very well. Okay, anyway, so when we're looking at this particular function, everything kind of looks sideways. So what we're going to be doing is we're going to set up our integral with respect to y. Okay, we're going to switch it all up. We just have to make sure that we switch it all up with the same logic, okay? And so in this case, let's go ahead and find our intersection point. Okay. Even though this is with y's, I argue we can use the same idea. How can we set this up to find the intersection point? Like, what is the setup so that we can find where these graphs cross? Set them equal to one another, perfect. So I get y squared minus 9 equals 7y minus y squared. This is my orange one. This is my pink one. And we will use that same idea. Let's move everything to one side, set it equal to 0 and solve. And so we will end up with 2y squared minus 7y minus 9 equals 0. All right. Factoring, everyone's favorite, everyone's best friend, So factor, I know it has to boil down to this. Let's see, 9 and 1, so maybe 9 and 1. I need a -7 and a +2, and I think that works out. Okay, so what that tells us is that y equals 9/2 is one of the intersection points, and y equals -1 is another one of the intersection points. Okay. Now that means that this point down here has a y value of which one? What's the y value for that first point right there? That one's going to be the -1. Okay. And then for this point up here, this one will have the y value of 9/2. Okay. So when we set up our integral now, okay, you'll notice I didn't even write the x values. Honestly, I don't even really care about the x values. I'm not going to need them in my integral. Okay. So our area here, when we look at our sideways problem, it's going to be the integral. Oh gosh, the integral. Now, someone said, is it always the one that's to the left that's the bottom bound? What are our thoughts? What's the bottom bound in this case? If we're going to have all of this stuff with respect to y, what's the bottom bound? In other words, do we want to start down here and draw our rectangles up? Or do we want to start here and sort of count down? Which one makes more sense to us? See, we've got to guess the bottom bound would be 9/2. Okay, so if the bottom bound is 9/2, we're starting here and we're sort of drawing all those rectangles all the way down to -1. Okay. You could certainly do that. 9/2 all the way to -1. Okay. And if you did that, we would also need to figure out sort of what is our top function and which one is our bottom function. Which one of these do you think is the top function? Okay. Turns out when everything is sideways, none of them are the top function, but what we're looking for is rather which one is to the right, so which one is more positive, and which one is to the left, or which one is more negative. Okay, and so what we're going to do is we're actually going to have 7y minus y squared minus the pink one. And so this one and this one will serve as our two functions, where the purple rectangle goes from the orange one down to the pink one, goes from the orange down to the pink, from the orange down to the pink, from the orange down to the pink. Okay. Typically though, when we look at bounds, there's nothing mathematically wrong with what you have here. Okay. However, typically when we write these, we think about the smaller number, the more negative number on the bottom, and the more positive number on the top. Okay, so I'm going to go ahead and switch these bounds. We sort of want to start at the bottom and then count our way all the way to the top. Okay. So this setup piece, super, super important. I think at the end, it should end up with this as an answer. Okay. But again, I'll leave that computation piece to you. I think really focusing on that setup piece is where I think we need to focus our energies. Okay. All right. So I think the last piece for class will be, let's go back up. And let's sort of summarize what we're talking about when we say with respect to X versus with respect to Y. Okay. So I could modify this first sentence. Instead of saying rectangles are perpendicular to the x-axis, I would say rectangles are perpendicular to the y-axis. Yeah, exactly. Okay. And so the way we say that is our area will be the integral. Now, we typically call these C and D, just to know that those values are Y values, they are not X values, okay? And instead of saying top minus bottom, we usually say right minus left. And we want to seal this off with not a dx, but a dy. Okay, we can say that C and D are Y values. And we're typically given equations are typically of the form X equals things with Y. I know that's so mathematically accurate, but typically you're given equations that look like or X equals a bunch of things with Y. Okay, so those are some good clues to look for when you're thinking like, how do I know, should I do with respect to X or with respect to Y? Okay. So that being said, I think this is a good sort of ending point for today. I will sort of include some of the other setups in the notes before I post them, in case you want to look for a little bit more help on how to make those decisions. But I actually feel really good about the conversation that we had today in terms of like, and the questions that were asked about how do we know when we have more than one integral. I think those were really valuable pieces, okay? So beyond the decision making, it's a lot of practice, all right? Practice in 3 areas: drawing your diagrams, finding intersection points, and setting up and then solving that integral, okay? I would say of those, the least important is like the computation piece. I'm really looking more for the connection between the diagram, the intersection points, and the setup here. Okay. All right, so then, the balance of the sideways one will be a smaller number on the top and then a smaller number on the bottom and then larger one on top. Yes, Megan, that's a great way of summarizing that. All right, so folks, these questions can take quite a bit of time. I would encourage you to get started on quiz 14 while things are sort of fresh in your head. Maybe at least just draw some diagrams, maybe just draw some diagrams and find some intersection points. But I think using that while it's still fresh in your brain will help retain that a little bit more. Okay. All right, folks, have a great rest of your day. I will see you on Wednesday.